Welcome back to Book Club. And before we go any further on what might be like chapter 3 of most thermo textbooks, I actually want to pause and just talk about what makes thermodynamics hard to most people. It's actually, it's not difficult. It's actually, we think we actually understand a concept, and in the end we don't. So what do I mean by that? Most people have a very good idea of what pressure is. You've been scuba diving and gone in the field, the pressure build up in your ears, or you've tried to open that can with a suction on it. So you have some idea of pressure. But most people also think they have an idea of temperature, and you really don't. So what we think we have an idea is actually heat. Heat is the thing that we naturally know about. And what do I mean by that? Well, let's think about 72-degree day, beautiful day. Would you go in 72-degree water? No, that's going to be freezing cold water. Why? Well, because water is going to suck the heat away out of you faster. It's a heat rate. I grew up in Canada. I knew that out in the winter, and I had my bare hand open, I could with my bare hand grab that branch, that stick, and be okay. But if I wouldn't grab that flagpole, good gravy, that was going to be really, really cold. Right? Or at the same time, maybe you've thought of like, well, it's a dry heat here in Arizona, it's not that bad, versus the like a humid heat, say here in Houston. So we always have these examples, and realizing it's actually what you're most naturally thinking of is heat. And so in the end, when we talk about temperature, really, it's yes, we can measure a thing called temperature, but usually what's happening is I have some block, and then I'm attaching to some block a thermometer, and what's really happening is I'm allowing just a little bit of energy to sort of come out of the system, so much that it's not really affecting the total energy of the system, and what it's going to do then is create that mercury to rise. So I can get a temperature. And then what people do naturally get pretty darn well is this idea of equilibrium. And so if I had two blocks, block A and a block B, that if A was hotter than B and I shove these two together, that you would very naturally understand that energy is going to flow, or heat is going to flow from A to B until the temperature of A is equal to the temperature of B. So this is equilibrium. And we do have a very natural way of thinking about equilibrium. So that's not a problem. But what's internal energy? Okay, so that's another one that if we go back up here and write internal energy, we don't have a very good idea of what internal energy is. Okay? And this is actually the way I'm teaching this course, the way I'm doing it. We'll do like sort of one little more bit out of sort of undergraduate thermo, but we'll have to come back to this idea of internal energy because we don't really understand what that is. In fact, there might be a molecule that's moving, and we would call that translational energy. And it might be banging around. Now, you could also have, say, a molecule that looks like a barbell, and it's rotating, and that would carry some sort of rotational energy. You could also have a molecule, like, here's like a water molecule, and it could be vibrating. These two molecules could be vibrating back and forth, sort of in their distances between each other. All of that's going to stack up into internal energy. And so this is where the physicists, when they talk about thermodynamics, they're really coming at it from a much more fundamental layer. They're going to talk about, I have a molecule, and then I have 10 molecules, and I have 10 to the 23, right, in Avogadro's number of work with molecules. And so that's an entire discipline which is called Statistical Mechanics. And what we're going to find by at least doing a little bit of flavor of statistical mechanics is that from statistical mechanics, we're going to have a good idea of two things that can come from this. Both, we will have a better idea of what temperature is, but more importantly, we're going to have a far better idea of what this thing called entropy is. And entropy, whenever we try to explain entropy, it always just kind of falls short when we're trying to kind of stay at this macro level of what is entropy. So we'll get there. We'll absolutely get there. And that's why we're going to take sort of a detour here in a second. But just priming you, we'll do like at least one more round and sort of an undergraduate thermal textbook before going away. Because there's still some good stuff that we can still come out of this. Right? And at the macro level, we do understand work. We've already sort of taken a look at that being the integral of P dV. We do get that one pretty well at the macro level. And then things like mass and volume, of course, are very natural aspects at the macro level. So next time we'll kind of do one more round here at that sort of undergraduate thermal book before we then dive a little bit into the world of statistical mechanics to try and come up with, honestly, a better understanding here of temperature and entropy, and then we'll see if we can't bring that back in. And again, it's not complicated. You usually just don't hear about it unless you've gone to grad school. In fact, one of my favorite quotes from my students was when he got into graduate thermodynamics and graduate fluid mechanics. He said, Andrew, I know what's wrong with education. I said, what is it? He says, it's that we do our undergraduate first. That's what's wrong with education. So dear reader, let's read through the rest of these books, and then we're going to kind of skip over into a taste of that kind of graduate level work. That'll make actually all of the rest of this fall into place much better. See you then. Okay, so last thing before we get into more of statistical mechanics formulation, right? Because like I said, we don't really understand that internal energy thing. But I do want to do sort of control volume analysis. And what we're talking about here a lot of times is the fundamental law is attached to the system. So you might say the mass of the system and its time rate of change is equal to 0. But a lot of times you may have some weird system where things are coming in here or exiting here. So it can be a little nebulous. What is the system? And so this is called the Reynolds analogy. And ultimately, what you end up doing is you say this is our control volume. You come back through here and ascertain this is your control volume. And so then this whole thing would look like the time rate of change of rho d volume. And then you would pick up that surface integral of rho and then v dot dA. Now, like I was hinting before, we're actually going to come back and change all of this vector notation. We're going to clean it up into the Einstein notation for when we do more complicated things. It'll be look all right, and it's equal to 0. And so this is actually conservation of mass. And so, you can do a lot of really easy things with it. Like I'm filling up a bucket. How tall is the bucket getting if I have a leak in it? There's a whole range of problems that, honestly, like go grab your thermal book, go look through thermal examples, look through some of those problems. Basically, all of it is just this. And then, yeah, it may simplify. Like you may this may end up looking like rho 1 v1 a1 plus rho 2 v2 a2 equals 0 or something. Like this integral could really simplify down. But my challenge to you is to kind of keep your math high, keep it at this level. And if this integral happens to pop down to something very simple, then God bless. Okay? And what we're going to find, honestly, is we could come back here, and I'm going to insert the letter B into each one of these here, and then it's going to be equal to something question mark here. And so what we're going to see is that if B equals 1, then this is conservation of mass, and we already just did that. If B is equal to a velocity vector, and this is why we're going to have to introduce Einstein's notation, is because you're going to be like, what velocity vector, what is being dotted with what? That's why we're going to come back and do this. This is conservation of momentum. And by the way, that right-hand side here was 0. The right-hand side, when we do conservation of momentum, is the sum of the forces. Okay? And then if B is equal to, and I'll write it like this, internal energy plus 1/2 V squared, kinetic energy plus GZ, that would be sort of the energy system. This is conservation of energy. And it's going to be equal to heat minus the work rate. And so there'll be a few manipulations. And we're actually going to focus on this last one here in particular. I'm going to write it out a little bit longer here because I actually want to introduce you to your first sort of other state variable. And then we're going to go then, from there, we'll then go to dive into the world of statistical mechanics. So let's write this out. So the line here, if I'm writing out conservation of energy, so that would be the time rate of change, and this is the energy, right? So U plus 1/2 velocity squared plus GZ, and that's across my control volume, plus the flux. And I'm going to give myself some room. You'll see why. U plus something's about to come in here. 1/2 V squared plus GZ. And this is V dot dA. And that's going to equal to Q. I mentioned, we know what Q is. We have not yet split this into temperature and entropy. We'll come back to that. At the moment, though, this would represent both what we would say the work and the control volume. But if you go back to here, and there's a pressure here associated with this, and there's a velocity taking the fluid across. So there's a pressure here associated with this, and a velocity taking the fluid across. So I also have a minus integral P dA. And so, boy, I have surface integral here and surface integral here. Wouldn't that be nice to combine the two? Well, that's actually really easy. Oops, I forgot on both of these, there's a density. Density times all that. Okay, so now we're good. Well, this term is actually just the same. I can take a density, as long as I undo the density. Remember, 1 over density is specific volume, the area. Well, isn't that convenient? So that's just going to circle back over here, such that this term is the contour integral of U plus PV plus 1/2 velocity squared GZ V dot dA. And this is equal to Q dot minus WCV, and I'll go ahead and write the time rate of change part, rho U plus 1/2 V squared plus GZ D volume. All right, so that whole thing is now conservation of energy, but I want you to take a look at this term, U plus PV. We're going to see that a lot, and your undergraduate textbooks would say, hey, this is just a term we see a lot. That's it. That is true, you're going to see this a lot. This is actually the roots of a variable change, okay? And we're going to see a couple of these. So depending on what problem you're solving, you can take a look at all of these different pieces. Now, one of the more important parts about thermodynamics is you only really need 2 things to specify a state. And so here before, we might have been talking about internal energy. And let's say I knew the temperature and pressure. I could go look it up. I could go look it up in the tables in the back of the textbook. I could go look it up in RefProp, any of those things. But there's actually a whole host, as long as I know 2 properties, right? I could know temperature and specific volume. I can know entropy and pressure, right? As long as I have 2, I can actually look up this property is fully defined. Now, we're going to get a little more rigorous and say sort of what are the natural variables of U. But pressure and V, this is just another one. So this is also a thermodynamic state. So I can also, if I know temperature and pressure, I can look up enthalpy. And so there'll be many, many problems where actually enthalpy is the correct thing to use. Why? Because it's actually the one here in the equation. And you're totally welcome to go use internal energy if you're solving this kind of a problem where you have things coming in and leaving. You can go do that. You're just going to have to do the mechanic of then adding in P times specific pressure times your specific volume. Or you can just look up enthalpy. So one sort of easy example of this is, let's say you have a throttling valve. So you've got some sort of throttling valve coming in that can come in, it can close up this flow completely, or it can carry it on. Now in this situation, if you're solving this problem, you may say it's insulated, and so that's going to say, okay, I have no heat transfer. There's no work coming out of this control volume. So both sides of this are zero of this equation. There is no time rate of change, so the first part goes away. If the area is the same, then we actually know, say, V1 here is equal to V2. And so the kinetic energy sort of on both sides of this contour integral, basically this contour integral is going to give me an integral over here at 1, an integral over here at 2. And I'll have to make sure my V dot dAs. And so no elevation change. And so honestly what you're left with is that H1 is equal to H2. However, P2, here's P1. However, P1 is greater than P2. So this is the throttling valve. And so throttling valve is enthalpy is conserved, pressure goes down. And so fairly easy way to do it. Another interesting example I'll kind of put up top and then I'll kind of hedge it. If you've ever taken a can, kind of like this can I've got here for kind of cleaning off the board, and I spray it. If I hold it long enough, right, or it's an air can, it's going to get cold. Why is that? Well, it's because if you do this whole analysis again, you've got a can, let's say you've got some liquid in here, and you've got some sort of valve that you open up, you spray out. And so, same thing's going to happen here. You have, in fact, in here, this is an internal energy. This would be the time rate of change of internal energy, but what's coming out, you would use enthalpy. So I actually really encourage you to go walk through this math, because what you're going to end up seeing is that for this to work, you end up having heat coming in. And that's exactly what happens, like the can gets cold. Or if you're cooking with propane on your propane grill, right? Your propane, your liquid is lowering. Why? Because it's boiling. Well, how is it boiling? Well, it's boiling because it's actually pulling heat. Why is it doing that? Because when you release the gaseous propane, there's a difference between H and U. Remember, H is U plus PV. So H is going out, which is always greater than the U, and so this thing's getting cold. Okay? So these are all examples of things you can solve in thermodynamics. That's what makes this a ton of fun. And then again, I would encourage you to look at these equations. None of them are actually incredibly hard. Really, this is just sort of conservation of mass, conservation of momentum, conservation of energy. And that's why here in a few videos, I'm actually going to introduce the Einstein notation, which will help actually make this not quite as burdensome, especially when we start doing a little bit more manipulations. But don't be afraid, right? In fact, the best students I ever had in my class are the ones who are not afraid to sort of, write this equation down. Like, this is your conservation of energy. And then you can quickly do, like we did down here, you can quickly be like, that's 0, and that's 0, and that's 0, and this is the same. And then in a simplified system like that, contour integral is just 2 locations. I do the 2 integrals. Oh, everything's constant. Nice and easy. So we'll see you next time as we begin a little bit of the journey downward into statistical mechanics and kind of kinetic theories of gases, so that we can come back to this thing right here. This cube, we have a good idea of what heat feels like, but we have yet to figure out how to handle this from a calculation point of view. And that's where we're going. See ya.